Hello everyone. Today we are going to discuss about thermal noise, Johnson noise, white noise, and equivalent noise resistance. So these topics are coming under communication theory. Within that, we are going to analyze about different noise characteristics. So here we know that the first one is thermal noise and Johnson noise. So in this noise generally generated in the conductor, resistor or active devices because of random motion of electrons. So if the motion of the electrons increases, the noise will increase. So that we are going to discuss in this particular video. Then when we are going to transmit a signal from one person to another person through a communication medium, the transmitted signal will be traveled through communication channel. That communication channel may be wired or wireless communication channel. In this wired or wireless communication channel, the wired channel noise domination is less. But in wireless channel, the noise domination is more because of the external noise will be more dominated in the wireless communication system, like man-made noise or industrial noise. That noise will be falling within the communication range of the station. That signal will be received by the receiver. So the receiver will receive both transmitted signal and also the noise. So because of this noise, the receiver will be affected while detecting original message signal. The final demodulated signal quality will be reducing because of the noise. So similar manner, then we are going to discuss about the different amplifiers are connected in cascade. So the resistors also available, R1, R2, R3 resistors are available. So here, because of this noise resistance R1, R2, R3, what is the equivalent noise resistance will be calculated. How to calculate that particular equivalent noise resistance? So that we are going to discuss in this particular video. Before discussing about thermal noise, first of all we are going to discuss about noise. So here already we are specified the transmitter section is available. With the information we are going to modulate and transmit by using antenna through the free space. So here the noise will be automatically added with the channel. The receiver side, it will receive both noise and also message signal. The demodulator will detect the original message and also the corresponding noise will also interfere or added with the original information signal. So here you can see the original message signal is available. The possible noises will be added together. Finally, the receiver will receive both message signal and also this noise. This noise is superimposed on the message signal based on the frequency band. So the noise is defined as the unwanted signal that tend to interfere with the required signal. Obviously, the noise is the unwanted signal that will be interfere with the original information signal that will reduce the quality of the communication system. So it is also defined as an unwanted electrical energy that fall within the pass band of the signal. For example, I am considering one radio station is available. That radio station transmitting frequency starts at F1 and ends at F2. In this particular band is called pass band for that particular radio station. So upper cutoff frequency and lower cutoff frequency. Within this band, if the noise is entered, because the thermal noise will be available in all frequency from minus infinity to plus infinity, irrespective of the frequency. In that particular situation, in this particular band, the thermal noise will be definitely available. Okay. So that noise will be automatically added with our original information signal, plus external noise like man-made and industrial noise will also added if it is falling within this frequency band. Then this frequency rise to audibility or visual disturbances in the communication system, error in digital communication. If noise domination is more, then what will happen? While receiving the audio signal, there is a disturbance or distortion in the corresponding audio signal. Similar manner, in the video signal, the visual quality will be affected. That is represented in this particular picture. Because of the noise domination, the video quality is reduced in this particular picture. Sometimes that flickering will happen in the video while you are watching the television. That and all because of the noise domination. So first of all, we are going to discuss about thermal noise or Johnson noise. This thermal noise or Johnson noise means normally in a conductor or a resistor or a active devices, the majority carriers are electrons. In that, if it is a n-type material. So in that particular situation, the electrons are moving from one place to another place based on two factors. One is based on applying external voltage. Another one is called thermal energy or heat. If the temperature increases, the random motion of the electrons will increase. Because of this random motion of electrons, it will be collide between one electron to another electron. The collision will happen. That will introduce noise in the communication system. That is called internal noise. So like this particular type of noise will be increased directly proportional to the temperature and also the bandwidth. This is calculated by using the formula. The average thermal noise power is given by Pn is equal to KTB. So here K representing Boltzmann constant, T is temperature of the conductor in terms of Kelvin, and B is representing bandwidth of the noise spectrum. Here K constant and T and B will decide the thermal noise power. So temperature increases, the noise power will increase. Bandwidth increases, the noise power will increase. Similar manner, if both the parameters are reducing, the noise power will reduce. Similar manner, we can calculate the thermal noise voltage also by using this formula, that is called En is equal to root of 4kTBR. So by using this particular formula, we are able to calculate the thermal noise voltage. So this is also called as RMS value of the noise voltage. Then similar manner, we can calculate the current, thermal noise current. RMS thermal noise current is given as IN is equal to root of 4kTBG. Instead of R, here we are replaced as G conductance. Okay, by using three different formulas, we are able to calculate power, voltage and current based on the noise. So then by using that formula, so one simple problem we are represented here. A receiver has a noise power bandwidth of 12 kilohertz. Receiver has a noise power bandwidth of 12 kilohertz. A noise resistance which matches with the receiver input impedance is connected across the antenna terminal. What is the noise power contributed by this resistor in the receiver bandwidth? Assume temperature to be 30 degrees Celsius. So here we have to calculate the noise power contributed by this resistor. So already we are familiar in the previous slide, they are represented the noise power, average noise power Pn is equal to KTB. So here the parameters provided is bandwidth, 12 kilohertz is the bandwidth, the temperature 30 degrees Celsius. So they are provided in terms of Celsius, we have to convert it as Kelvin by adding 273 with your degree Celsius. Finally it will convert as 303 degree Kelvin. substitute both the values, and also K we are familiar, it is constant 1.38 into 10 to the power minus 23. Finally, the noise power because of the resistor 5.01768 into 10 to the power minus 17 watts. So because of that resistor, the average noise power is this particular value. So the next one is noise calculations in series connection of resistor and also parallel connection of the resistors. So what is the corresponding thermal noise voltage? So how to calculate it? So the noise resistor acts as a source of thermal noise, so that let us see the effect of connecting two noise sources or two resistors in series. So you can see R1, R2, two resistors are connected in series. R1, R2, the corresponding voltage generated or noise voltage generated because of the resistor 1, En square equal to 4kTb R1. Similar manner, because of R2, the noise voltage generated is En square is equal to 4kTb R2. So the equivalent noise, thermal noise, if you are connected in series, we can combine together R1 plus R2 will be represented as R. So the resultant noise voltage is En square is equal to 4kTb R1 plus R2. So here the formula represented to calculate the total noise present in the series connection of the resistor, En square is equal to 4kTb R. This R is replaced as R1 plus R2. So if you want to calculate separately, 4kTb R1 plus 4kTb R2. This will be replaced as En1 square and En2 square. Now En is equal to total square root of En square plus E2 square. Since two resistors are in series, they can be replaced by a resistor R instead of R1 and R2. So the noise voltage generated by the resistor R is given by En is equal to root of En1 square plus En2 square. Thus the equivalent noise voltage of the series combination of resistors is equal to vector sum of noise voltages produced by the individual noise resistance. So the equivalent noise voltage of the series combination of resistors is equal to vector sum of individual noise voltages of because of the resistor R1 and R2. Similar manner, we are going to calculate what is the noise domination if the resistor is connected in parallel. For the parallel connection of resistor R1 and R2, the current equivalent circuits are used to. You can see the corresponding circuit diagram. The conductor G1, inverse of resistance, is called conductance. So G1 and G2, the two conductance are connected in parallel. Because of this resistor 1 and resistor 2, the equivalent noise current I1 square is equal to 4G1 kTb. Similar manner, IN2 square is equal to 4G2 kTb. So here, when you are going to combine together, the equivalent circuit is Gp is equal to G1 plus G2. Because of the conductance 1 and 2, the equivalent noise current is IN2 square is equal to 4 Gp. Gp is called G1 plus G2 kTb. So the two conductance G1 and G2 are in parallel. The effective value of the conductor is Gp is equal to G1 plus G2. So the current due to this both the conductance G1 and G2, this will be replaced as 4 G1 plus G2 multiply with kTb. Okay. So similar manner, the total current IN square is equal to I1 square plus IN2 square, so on. So whatever may be the n number of resistors connected in parallel, By using this particular formula, we are able to calculate the total noise current IN square for how many number of resistors. You can put it as G1, G2, G3 and so on, Gn and KTB. If it is required to obtain the voltage generated equivalent circuit for the parallel connection of resistor, then the equivalent parallel resistor is resistances Rp is given as Rp will be represented as 1 by R1, 1 by R2, 1 by G3 and 1 by R3 and so on 1 by Rn. This 1 by R1 1 will be represented here as G1. Okay, so now in terms of resistance itself, we can represent it as 1 by R1, 1 by R2, so on. Now we are calculated what is the effective resistance Rp. So by using this voltage formula, we are able to apply this Rp. We can calculate the noise voltage. En square is equal to 4 Rp KTB. So this is the final formula to calculate your noise voltage if the resistors are connected in parallel. Now we are going to discuss about white noise or Gaussian noise. What is mean by white noise? White noise is the noise whose power spectral density is uniform over the entire frequency range of interest. You can see the first corresponding picture representing from 0 to minus infinity and 0 to plus infinity and 0 to minus infinity. The entire frequency range, the power spectral density is constant. The value is N0 divided by 2. So that means this corresponding diagram or picture representing power spectral density representing the white noise or thermal noise is present in the entire frequency range. The white noise has Gaussian distribution. That means the power distribution function of white noise as shape of the Gaussian power density function. Therefore it is called therefore it is called as Gaussian noise. Power spectral density of the noise is Sn of f is equal to N0 divided by 2. That is already represented in this diagram. The equation shown that the power spectral density of the white noise independent of frequency as N0 is constant. So there is no frequency component here present. It is the power spectral density is independent of frequency. So the power spectral density is uniform over the entire frequency range including positive as well as negative frequency. Then this white noise will be measured or calculated in terms of autocorrelation function. So in the autocorrelation function of white noise, any two samples of white noise are totally uncorrelated. So we can calculate correlation by using two factors. One is called cross correlation, another one is called autocorrelation. The cross correlation means the correlation or similarity between two different signals. Autocorrelation means we are going to identify the correlation between one point of the signal to another point of the signal, that is within the signal, within single signal itself at different time slot. What is the correlation or similarities available, that will be calculated by using autocorrelation. As per this particular noise, Johnson noise or white noise, you can see at time t1 and time t plus tau there is no correlation. Similar manner time t2 and time t2 plus tau there is no correlation. So each and every time instant the noise is continuously varying. There is no similarity. So that's why the autocorrelation function is represented as here N0 by 2 at time 0. So each and every time instant the corresponding the similarity of the or nature of the signal is different. So that's why the autocorrelation is N0 divided by 2 at time 0. So R tau is equal to N0 divided by 2 at tau is equal to 0. This is the white noise autocorrelation. Then we are going to calculate noise due to several amplifiers in cascade. So by using this particular diagram, we are going to calculate equivalent noise resistance. You can see here the corresponding two amplifiers are available. A1 and the amplifiers are available 1 and 2. A1 representing gain of the amplifier 1 and A2 representing gain of the amplifier 2. So here the input noise is represented as R1, the noise voltage is VN1, and input noise to the amplifier 2 is R2 and the corresponding noise voltage is VN2. Similar manner, output of the amplifier 2 noise is R3, represented as R3 and EN3. So this R1, the noise resistant generated voltage is VN1, R2 noise generated voltage is VN2, R3 noise generated voltage is VN3. So here if the noise voltage is VN1, if you are applying to amplifier 1, what will happen? The original information signal and also this noise will be amplified with the gain factor of G1 or your A1. So this amplified noise and the noise generated due to R2 both will be added together. Then this noise will be applied to amplifier 2. Then again this amplified noise because of the amplifier 1. Second time it will amplify by using the gain factor A2. Then again the amplified noise you are able to get at the output of the amplifier 2. Then this particular circuit will be analyzed or replaced by combining all resistors together. How to calculate the equivalent noise resistance? In the receiver, as a number of multiplying stages or connections in cascade, you know that RF amplifier, mixer, IF amplifier, power amplifier, matching network and so many blocks will be connected in cascade. To find the combined effect of such connection on the receiver noise, the gain of the two stages here they are represented as A1 and A2. The first stage as a total input noise resistance R1, the second stage as the total input noise resistance R2 and the output noise resistance is R3. So now the RMS noise voltage at the output due to R3, the output noise voltage is VN3, the corresponding value square root of 4kTB R3. So the RMS noise voltage VN3 is produced due to the RMS value of R3 dash at the input of the second stage. This noise is due to the corresponding VN3 dash. So that will be amplified by using this amplifier A2. Okay. So that's why VN3 is divided by A2. VN3 is the total output. This total output because of the gain factor of A2. So that's why that amplification factor is divided. VN3 divided by A2, you will get VN3 dash. So the VN3 dash is equal to, just we are replacing this corresponding VN3, the square root of 4kTB R3 divided by A2. Then again we are rearranging R3. If the square root is extended here, what will happen? You will get A2 square. So R3 A2 square, this is represented as R3 dash, combining together. So then therefore the equivalent noise resistance at the input side, then we can transfer this R3 resistor to input side of the amplifier. So that's why R dash equivalent equal to R2 plus R3 dash. R3 dash we are already calculated here. Just we are going to substitute here R2 plus R3 divided by A2. Similarly, we can transfer this R equivalent here R2 plus R3 dash is available, no? That we have to transfer input of the amplifier 1, sorry, output of the amplifier 1 to input of the amplifier 1. So then we have to again divide by using the gain factor A2. So now total R equivalent divided by A1 square. You know that R equivalent is already calculated here. Just substitute here. You will get R2 divided by A1 square plus R3 divided by A1 square into A2 square. Because of this A2 you are getting here also. So then similar manner we are going to calculate what is the R equivalent. This R3 dash will be added with R1, that is the equivalent noise resistance. So you can see here R equivalent equal to R1 plus R2. Now we are already calculated what is your R2 dash. So here dash is missing R1 plus R2 dash. So the R2 dash is R2 plus A1 square plus R3 A1 square into A2 square. This is the equivalent noise resistance. So if you are connected n number of resistors in the cascaded form in the with the amplifier, then what will happen? The noise will also amplified because of the amplifier 1 and 2. Then we can calculate the R equivalent resistor if it is cascaded amplifier. The same concept is applicable for the n number of amplifiers if you are connected in series or your corresponding cascaded form. Okay, so that's all. Today in this video we are discussed about thermal noise, Johnson noise, white noise and equivalent noise resistance. What will happen if the resistors is connected in series and also parallel, and the same if you are connecting in a cascaded amplifier stage, what will be the equivalent noise resistance we are discussed in this particular video. So I think this particular video useful for you. If you like this, you can like, comment, share and subscribe. So thank you for watching this video. Thank you all.